So today there's a seventh lecture on invariant maximal reversal by Harvey Friedman. Please.
Thank you. All right, so we're making progress here. Let's see where we are. Just a second, let me move this screen over. There we go. Yeah. Okay, so last week we didn't have a lecture. This week we do. Okay, so uh, the previous lecture 6 is on the downloadable lecture notes page. Also, the actual lecture recording is on Andreas's page that he uses for this purpose. And uh, I put up sections, polished versions of sections 8 and 9 of the reversal on the downloadable manuscripts page, and the stuff on the downloadable lecture notes page from which I lectured, probably lightly edited. But the master one, of course, is the one on the downloadable manuscripts page, which always has a lot more details than the what I do in the lecture. All right, so now we're going backwards because that's what we decided would be best. So we did 11, 10, 9, 8, and now we're going to do 7. And recall that what we're reversing is this statement, whose notation and meaning has been fixed for quite a while. Every order invariant graph on q minus 1, 1 to the k has a invariant maximal clique, where this is the function that creeps up. 0k goes to 1 over k, 1 over k goes to 2 over k, dot, dot, dot. K minus 1 over k goes to k over k, and it's the identity below 0. And of course, if I didn't put the identity below 0, if it was just this shift map, so to speak, then it would be provable, although not that easy to prove because of the endpoint. It would be provable in a weak system, relatively weak system. I think ACA prime is enough. I'm not, yeah. Certainly ACA with full induction would be more than enough, but somewhat weaker than that. All right, and now remember that this is the table of contents for this crucial reversal chapter of the book. And as I said, we did 10, 11, 10, 9, and 8. Today we're going to do 7. This is a bookkeeping section, which is you'll see what I mean at some point. I may flash some of this up, but it's the most boring thing possible. And so therefore, next week we do tupling. Some of this was discussed somewhat earlier, but before I got really systematic here. Next week is tupling. The week after is negative reduction. The week after that is atomic representation. Probably I should give a lecture on this background stuff. I have to see how I want to talk about this when we really get close to the end. Exactly how the lecture should work. Maybe after negative reduction, it might make sense to just do 1, 2, and 3, because this one was already talked about some, and it's not that long, not that complicated. So I have to decide how do we want to do that. Okay, so as usual, we have to back up a little bit. So this is not relevant. We have to back up to the end of 4.5 so that we can start this with some knowledge of what's happening. So the end of 4.5 really is enough for the start of 4.7. I think without any ifs, ands, or buts. I think that's smooth. That's a completely smooth transition. For putting this aside. Um, so section 4.5 ends with this structure, and the whole of section 7 is just about this same structure. All I want to do in section 7, and it's a pretty big deal. All I want to do in section 7 is 4.7, so to speak, is in fact there's a kind of very weak light phase separation at the end of section 5, 4.5. There is this weak light phase separation. All the chapter 7 that we're going to do today, the only whole point of it is to derive full separation. By full, I still mean bounded quantifiers in the structure, but full separation with parameters. You'll see how weak the separation is. I actually call it representation is from section 4.5 in about a second from now. And all we want to do is get it to be full separation. We won't even improve the indiscernibility. We won't even improve the indiscernibility. The indiscernibility will not be improved. Just the separation will be improved. I think that's all I do. I think that's it. All right. So the end of section 5 ends in theorem, the end of section 4.5, so to speak. Chapter 4, 4 means chapter 4. The end of section 4.5 is this. There's a structure M whose domain is the non-negative rationals under the usual order with a k-ary relation on the non-negative rationals with the so-called indiscernibles 1, 2, dot, dot, dot. It has the following properties. This is the end of section 5. It has the following properties. Tupling, some weak form of separation called representation, and indiscernibles. Nothing else. That's it. And tupling says the following. If I have a k-1 tuple, then there's a unique p that codes it. P greater than the max of x, such that R of px. And if x and y, so there's a kind of weak one-oneness that's very important to say right. If I have two k-1 tuples with the same max and the same unique p, then they're equal. See, naturally, you would want it to be 1, 1. It just simply that if they have the same unique p, then they're equal. But that's not, I don't get that. I have only this weaker one, that if x and y have the same max and they have the same unique p, then x equals y. And if max of x is less than n, then this unique p is less than n. This is also holds at the end of section 5. So this causes some complications that I don't have actually full 1, 1. It causes some complications, but I know how to handle this nicely. So it didn't. It was something that I can. You'll see how I handle this. All right. So here is this form of separation or representation. Suppose I have a formula. Now, this is the language, that we've been talking about that I use a lot. It's the finite language I use a lot. So I have a formula in this language, and I have a number n greater than or equal to 1, then then there exists five uh, numbers below n plus 1, such that for every x in Qn to the k, phi holds at the assignment x stretched to be of length k1, quantifiers restricted to less n, if and only if R of x p1 through p5. Okay. You see, x is dimension k minus 5. That 5 obviously should be over here, except that we've got typesetting puts the 5 over here. It's part of the exponent, you see. So this is a light-faced thing, you see. I'm taking the set of all x such that something holds without parameters, and I'm saying that I can rewrite it atomically with five parameters. In set theory, you got a formula and you actually get something with one parameter, namely the set that's being separated. Here we have five parameters. And of course, instead of a binary epsilon relation, we have a K area relation R. Okay, so that's the kind of very weak separation we have. We want to get the full thing, where we don't use this language, we use the full language L of K, and we want X to be arbitrary length. You see, this only works in space. In this only works. This statement only works comprehending uh, comprehending up in dimension k minus 5. We want arbitrary dimension, and we want arbitrary formula. We don't want just this finite language. And we want this. Actually, we want something a little more technical, a little bit finer than this, but basically this. And uh, we have to go through quite a bit to do that. All right. The indiscernibility is, never mind this noise. The indiscernibility is basically looks like this. Uh, Phi holds that indiscernibles D1 through D K1 minus I, if and only if you can move the indiscernibles, just make sure that they have the same order type. And the superscript has to be legal, bigger than the indiscernibles, but they can be any numbers. Uh, and this is the parameters below the indiscernibles, same parameters X. See, max X is less than the minimum of everybody, minimum of all the indiscernibles. So this is an expected form of indiscernibility. And we don't attempt to improve on this um, in section 7. If you recall, before we do manage to improve on this, at some point we managed to have it for all formulas, not even for the finite language. I mean, but that's much later, and that was much earlier in this lecture series. That was a few lectures ago we did that. All right. So this section 7 is called M equals Q0 infinity less than R 1, 2, dot, dot, dot. Um, okay. We always use this finite language, but there's also the infinite language, L of K, which is just less than an R and arbitrary quantifiers and arbitrary complexity of quantifiers and connectives. So the goal is to go from a form of parameterless separation to an expected form of limited separation with parameters. Indiscernibles is not upgraded, as I said. Yeah, I guess I just repeated this because yeah, because it's repeated in the manuscript from section 5 to section 7. All right, we already did this. Same thing, just copied. And this M is the only remnant of sections 1 through 6 that remains, which is nice. We continue to use this fixed K. K is fixed until the proof of theorem 10.2, if you recall. So we want to get an upgraded version of this separation or R representation /1. I call it R representation /1 because there's R representation /2, R representation /3, and then we jump to limited separation, which is the goalpost. Um, maybe limited separation /M, I call it. So limited separation /M means every Q less than N and M greater or equal to 1, every subset bounded by Q here with an arbitrary exponent that's LK definable over the structure Q0Q less than or equal R under this structure with parameters less than Q is explicitly given by a certain special simple construction of low complexity called set of QUM, which we define as we proceed. Yeah. So we don't get that we're comprehending or separating the set in question as simple as this. This is really simple. It's just that. It's not quite as simple. It's a little more complicated. All right. Now in M representation /2, so this is all introductory. We actually explicitly go into what these things say more formally. The subsets of dimension at most k minus 7 defined in a little bit lower language. In other words, k of 1 over 2 of variables, complexity k over 1 divided by 2, still with just a k area relation symbol. With at most k minus 1 parameters below n. This time we really do have parameters, are atomically represented using parameters P1 through P7 less than or equal to n plus 1. And we need some infrastructure will push us up to need 2 more parameters, 7 instead of 5. None of that is important. And we use the explicit construction capital set of n um in dimensions m less than or equal to k minus 7. To achieve this, we use a very direct pair coding of tuples of length only less than or equal to k minus 1 from tuples above. Okay, pair codes are ordered pairs. See definition 7.3 would do that. Every tuple of length less than or equal to k minus 1 has a unique pair code. So we will need codes, but we won't be able to talk about codes till quite a bit later of arbitrary length, which we will need. We will only be able to talk about codes of length at most k minus 1, right? Fairly easily. And by the way, all codes of tuples are actual pairs. I know that sounds strange, but the codes for tuples of rationals are going to be pairs. This comes from the fact that our tupling, if you remember, was not 1, 1. It was only 1, 1 relative to each sphere. In other words, it was 1, 1 on the tuples of a given max. That's why we do these strange things like having tupling of rationals be pairs instead of just a single rational. All right. Yeah, these pair codes are ordered pairs of rationals. If two tuples with the same length and most k minus 1 have the same pair code, then they're equal. Okay, the third version of separation treats subsets of the still just dimension at most k minus 7 in a little lower language, not too important, dividing by 8, with at most k minus 1 parameters. Um, Now, let me just see. What was I just saying? Just a second. Oh, yeah. Yeah. In representation 2, we work in Q0N. In representation 3, we do something that we need to do, which is we work in the Q0K, 0Q to the M, where Q is less than N. See? Okay. So the representation, the second version, you're actually separating out all the way up to N. But in the third version, you're only separating out up to a place below N, uh, and you get a representation below N. Okay. And in both cases, though, you make this move to seven uh, I hate to say parameters because that might mean parameters in the front end. No, and 7 back end parameters, so to speak, seven items. All right. Now we really have to work with finite sequences of arbitrary finite length, sequences of arbitrary finite length, which is a problem. We need some work to be able to do that. We have to bootstrap this up. And well, a preliminary step is that in dimension at most k minus 7, if you look at these explicit sets that I use for the separation, these are shown to form a Boolean algebra of sets in each dimension, m less than or equal to k minus 7. These are shown to form a Boolean algebra of sets with the help of a very weak application of m indiscernibles. You will need some indiscernibility to do that. The partial function uh, as graph set of QUM as shown to, is shown to be is shown is shown to be closed under composition. Uh, I should say the partial functions as graphs uh, given by the set QUM is shown to be closed under composition, and the projection functions of the are the form set of QUM. Okay, not sure I said this too well, but you get the idea. Now, to make further progress, we need to treat tuples of arbitrary finite length. And for this, we need a convenient pairing function. So far, I haven't really talked about uh, the right kind of pairing function. So we don't have a pairing function on Q0 infinity, meaning given 2 points, I find a third point. However, we do have a convenient pairing function, which is demonstrably 1, 1 on pairs. So we have a pairing function on pairs. This is how I get around things. I use this, which is 1, 1, but not onto. We also use the inverse pairing functions, f and g, for this pairing function. These are all partial. And then we defined P star of alpha 1 through alpha m, where these are pairs for every m by iteration, usual iteration. And we represent f and g by set of QU4 Uh, it's four because F is a mapping from pairs to pairs. So the graph is a four-dimensional set, and therefore it's of that form from the representation we have. We say that Q is closed if any two elements below Q, the P of P1, P2 has both coordinates less than Q. Remember, this is going to be itself a pair. The actual codes are always pairs. Now we use the low dimensional F and G. Remember, those are inverse functions of a pairing function on pairs. So these are still low dimensional, and it's arbitrary straight line composites to treat arbitrary dimensions. And so we define PC star of P1 through PM to be an ordered pair. It's called the pair code of P1 through PM. And we define set of QUM in all dimensions using this PC star. In other words, we formulate constructions in higher dimensions, but we pull them back into low dimensions, uh, where we actually have representation already. And that's how I get representation higher up. Limited separation slash M is based on the full language L of K and treats subsets in dimension M defined in the full language with parameters less than Q. We first handle the case with no parameters and easily bring in parameters. The basis and induction cases on the formulas are handled in low dimensions so that we eventually pull back to representation. Now, indiscernibles is used in almost every step in this development. However, we only need very basic instances of M indiscernibles. We don't get close to stretching the full amount of indiscernibles we have, full power. We just need some. Note that the upgrade R representation slash one to limited separation M in this section. Note that we upgraded it in this section, but we do not upgrade M indiscernibles, as I said. All right. This is just some notational conventions, uh, which are obvious. Uh, all right, now, yeah, this is the most primitive kind of coding we do. Again, we have these more elaborate things. This coding only works in dimensions less than or equal to K minus one. We take the unique number greater than P1 through PM, such that R of P, P1 through PM repeated so that this fills out to the right number of arguments. And Q, the second coordinate is just the max of the numbers put in. And the first coordinate is the tupling that comes at the end of section 5, right? Under tupling, where we began. So you want to code a bunch of numbers. You take that P that's given right at the beginning of this lecture, but then you also have to put in the max. The second coordinate Q is actually the max of P1 through PM. Okay. And then that will be a 1-1 coding. If two sequences have a common pair code, they're equal. Yeah, that's what this says. Okay. Next is, well, we just made the construction, and this definition is just naming the construction PC, pair code. Now, PC is only a way of coding sequences of non-negative rationals of length less than or equal to k minus 1 as ordered pairs of non-negative rationals. But we need to find such sequences for arbitrary finite length after considerable development. And that will be using what's called PC star, an elaboration of PC, but making sense in any dimension. All right, now here's the definition of capital set. There's also an even more important when we leave this chapter 7, section 7, um, is set with little s, little t, little t. SET lowercase is a more advanced thing. This is the one that we use to explicitly define a set in a low-level way. This is the one we use when we're in low dimensions, m less than or equal to k minus 7. And we write set of q u semicolon m, it's understood that m is less than or equal to k minus 7, that u is a 7 tuple from the non-negative rationals, and q is greater than or equal to 0. And the significance of the q is that that's where that's where our given set is that we like to represent as capital set Q U M. Okay. Notice that this is atomically defined construction, very explicit construction. But again, only dimension less than or equal to k minus 1. We will develop a similar thing for arbitrary m after considerable development. Okay. Now, using our new terminology, we can restate a representation 1 as follows. Let phi be a formula in our limited language. Take the set of all x, the set of all k minus 5 tuples sitting below n, such that this formula holds, which is defined to be, well, this set, the representation theorem says that this set is actually equal to set of n comma u semicolon k minus 5. The k minus 5, the last number here indicates the dimension. U indicates the 5 parameters at first. Yes, 5 parameters. And the n above indicates how high up we're going. So we're going up to, but not including the nth indiscernible n. So you can see that M representation /1 is a kind of separation without parameters and only in dimension k minus 5. Yeah, I'm stating it only for dimension k minus 5. It's relatively easy to get it for less than or equal to k minus 5 using when we'll have to do that using dummy arguments. All right, but that's without parameters, and we would like to use less than k parameters. All right, so what do we do? The first thing we want to do is, so we may have a lot of parameters. Oh, by the way, and I'm only going to allow at most k parameters, so this is still pretty limited. The idea is that since I know how to write pair code for the y, remember the code PC of y is going to be a pair. Why don't I plug in why don't I plug in PCY here? In other words, instead of trying to go all the way from no parameters to K minus one parameters, let's go from no parameters to two parameters, namely PC of Y, where Y is a less than K tuple, is always going to be a two a two tuple, an ordered pair here. Okay. So you can, from the code, you can get unwinded and definably without changing much. So this is just a straightforward relativization. And now, once you have that, you can apply R separation slash one using lemma 473. You get lemma 474, which is R separation slash two. And this says that if M is the most K minus seven and Y is a less than K tuple from 0 through N, and phi is a formula uh, in the half language, then the set of all X in Q0N to the M such that SAT holds is set of NUM for some U. That's what the representation says. So it's just basically what we had before in representation one, except that we're allowing less than K parameters. Yeah. All right. Now, we would like to have a version of this where the sets are subsets of Q0Q. In other words, where Q is less than N. We'd like to have the separation not go through the whole all the way up to the nth indiscernible, which is that, but up to any region below it. And so that's what this says. We need a technical level to actually prove it, but minor. This is just kind of nuisance work. It's has to be done, but it's ugly. It's kind of basically simple, but writing it down properly is a little bit harder. All right, so representation three, we're again in dimension less than or equal to K minus seven, and we have a formula, maybe it's 1/4 the old language, which is not important. Uh, then we take the set of all X in Q0K to the M sat, and I claim that it's of the form set QUM, where U is seven tuple. It's just like representation two, except N is replaced by Q. All right. Okay. So we basically going forward, we're going to always pretty much be using representation slash three for the most part. All right. Now, uh, let's see. When did I do the am I maybe that's done later. Just I was looking at something here. Let's see something. Wonder if I left something out here. Yeah, or maybe I glossed over it. Just a second. Maybe it's oh yeah, 477 is missing here. I didn't copy it from the original manuscript. This is a problem. All right, but I know what 477 is. 477 says that see, what we want to do is look at the family of all sets like this. Let's look at the family of all sets of the form set of Q, comma U, semicolon M, where M and Q are fixed. M is the dimension we're in, and Q is a number below N we're at. Then we look at all of the seven tuples we can plug in here, all the seven tuples in here, and we get a family of sets in M dimensions. And 477, which is missing here, I'm going to have to fix that before I put it in the downloadable lecture page. I wonder why that happened. All right. Anyways, uh, that set forms a Boolean algebra. 477 says that family of sets, that family of subsets of Q0K of dimension M form a Boolean algebra of sets. That's what 477 says. And 478 um, 478 says something similar about composition, that if you go to the partial function world where you are identifying things with graphs, that if if two partial functions are of the form set QU2M, right? It's going to be 2M because it's partial function from M tuples to M tuples. Then its composition is also going to be of the form set QUM. So it's closure under composition, you see? That's what 478 says. It's got another thing in there about projection, but that's a technical detail. All right. Now we need a pairing function on Q on the non-negative rationals, but we don't get it. Pairing function meaning one point comma point goes into a point. We don't have that, but we do have it on pairs. So P of Q0 infinity squared cross Q0 infinity squared into Q0 infinity squared is defined by P of the pair P1, P2, pair P3, P4 is equal to the pair code of the four tuple P1, P2, P4, P3, P4. That's how I get around things. That's the pairing function on pairs. And it's easy to see because of the nature of PC that we discussed, it's easy to see that this is 1, 1, well-defined in 1, 1. And then we want to take the inverses of this pairing function. This function is total. Yeah, we want to take the inverses. Now, the inverses are only partial because nobody said that this function P is onto. So the inverses are going to be partial. And they're called F and G, capital letters F and G. And these are defined in the normal way that you can define inverses. All right. We let Greek letters stand for these ordered pairs. It's convenient to have some letters reserved for ordered pairs. And then we define P star of beta 1 through beta M is just iterating the capital P function, which was our original pairing function on pairs, except this is iterated like this. Okay, so what's the next? Okay. P star of beta 1 through beta M is the unique gamma. See, P star is obtained by iterating. See here, iterating in the usual way from a binary function to a m-ary function. And the inverse of that is going to be the inverse of that is look like this: F gamma, F G gamma, F double G gamma, all the way to F G M minus 2 gamma, F G minus M minus 1 gamma, where this means iteration. See that more or less how that works. Also, P star is strictly dominating, meaning P star of a bunch of uh, numbers is greater than or equal to each one. The first coordinate, sorry. Remember, P star is a pair value function. So the first coordinate is going to be bigger than the max of all the betas. All right. Next, we define PC star. We have P star. We want to find PC star. And it's the same, except we apply it to this diagonal. The idea of PC star is now it's a mapping not from, see, P star was a mapping from pairs into pairs, a bunch of pairs into a pair. Here we want to map from uh, a bunch of numbers into pairs, and we can make the numbers work for us by turning them into pairs like this. Okay, and this PC star P1 to PM is called the pair code. Note that we use a hyphen to distinguish pair codes, pair hyphen code from pair code. All pair codes and pair hyphen codes are ordered pairs. PC star is our coding of finite sequences of non-negative rationals of arbitrary length by ordered pairs, whereas just PC was our coding of finite sequences of non-negative rationals of length less than k by ordered pairs. By lemma 7-1, PC is 1-1 in each arity. That's from tupling. And we see below that PC star is also 1-1 in each arity. Also in PC and PC star, the first terms of a value is greater than all of the arguments. Okay. Now the next thing is just some bookkeeping, but also it says that PC star is 1-1, even though it's a more complicated concept. It also has this this property. Now, PQ is simply called a pair code in dimension M, if and only if it's the pair code of some P1 through PM. And PQ of 1M through M is the result of applying FFG through FG M minus 2, G M minus 1 to PQ. All right. Lemma. So suppose I have non-negative rationals. Then PQ is a pair code M, if and only if I just wrote it in a different way, if and only if PQ of IM is some TT. See, these are diagonal pairs that are put in. All right, PC star of P1 through PM is the unique PQ such that each PI is PQ of IM. PC star of P1 through PM is the unique pair code M. And PQ with PQ in Q0 infinity squared, such that each PI is PQIM1. This is just bookkeeping between tupling and the inverse process, and the more complicated versions that work in any dimension. All right. How did I get any dimension? Well, that was done by this Boolean algebra and this composition of functions technique, because that's all low level. And then I can use that to bootstrap up. All right. So now remember, f and g are these inverse pairing functions on the pairs. So f is a partial map from pairs to pairs. G is also. And they are reducing, they're reductive, f and g. So that's why they're mapping that's why they're mapping 0 to q and 0 to q. And they're also of the form set QU4 and QV4. You see, these are Fourier relations, this F and G. So everything's fine here. All right, the next definition is closed. Obviously, we want to say that Q is closed if given any two numbers less than Q, the pair code is below Q. Of course, the pair code will be a pair. So both coordinates are smaller than Q. Now we want a lemma that says that there are plenty of closed points. Namely, if Q is less than N, then I can find a closed point strictly between Q and N. Okay. Now, if Q is closed, then PC star of Q0 QM is contained in Q0 QM. That's pretty clear because everything we did pushed things down. And when it did push things down, it was doing something with P. And yeah, so the way lemma 715 works is it's proved by, if I remember right, it's proved by there's some indiscernibility that's used in lemma 715. Because you can do this for n plus one and say that this must be true by setting q prime equals n, and then you can get rid of the n plus one and replace it by m. That's how you do that kind of thing. All right. This yeah. So here's the official definition of set. This is how we represent reasonably definable sets, ultimately definable sets, by explicit construction. This is very important to have this in any dimension. Here, the dimension m is arbitrary. We had it before. Now, it's exactly what we had before. What we had before was capital S, capital E, capital T, and we had R of X, U, star K. R of X, U, star K. Now we have R of PC star X, U, star K. See? That's the right way to do this. But we had to develop PC star, and that took a lot of uses of capital S, capital E, capital T in order to be able to do that. And whenever we write set of Q, U, semicolon, M, it's understood that Q is non-negative and U is seven things. Yeah. Okay. Now, the I'm going to quickly go through this because I'm running out of time, but a little bit more here. Uh, so we have a process. We have these these sets of higher dimension, and now we want to prove that they're closed under predicate calculus, basically. That's what we want to do. We want to prove they're closed under predicate calculus, if you know what I mean. Whereas Boolean algebra, closed under quantification and all that. And so we just slog through that. Uh, First of all, the set of master codes is the kind of thing we want. We need to yeah, this is the set of X in Q and 0Q2. So I think that, oh, is a pair codes. Yeah, yeah, that seems like this should be a 2 here, not of an M. Yeah, right. That's important. Yeah. All right. Now here we want to take care of the atomic formula case. We want to say that set of the set of points such that an atomic formula case, the set of assignments, so to speak, in for atomic formula case is of the form we want. A form we want means is it of the form set of Q, U, semicolon, M, with Q fixed and M fixed, where the 7 parameters can be various things, right? So this is the atomic formula case, and then we do the other atomic formula case. Yeah, this is atomic. This is the most trivial kind of atomic formula. Xi less than Xj. Here we look at the atomic formulas of this kind. Okay, and now uh, we want to do this is the existential quantification case, closure under existential quantification. That again, everything's of this form, set of V semicolon M for some seven tuple, for some seven tuple. All right, these are more closure properties. Yeah, this is a summary of the closure properties that we're going to get. And by the way, we are able to do that by pulling down to the dimension. Yeah. And so now we have the infinite language L of K, which is ordinary predicate calculus without equality, based on less than and the K area relation symbol R. And assignments now are of infinite length. Not that we're going to code anything of infinite length. We basically only care about assignments which are eventually constant. This is standard predicate calculus material where you try to avoid 2 to the aleph naught assignments. You just want countably many. Um, so uh, we want to show the set of all X such that SAT holds at the assignment X. Now the assignment X isn't really an assignment unless I make it of infinite length. So I use X sharp, which means you just repeat the last term forever. Is a set of the form that we want. See, we're getting very close to full separation. This is a fixing. This here is parameterless separation. Here we lift it to separation with parameters in the usual way. We just treat the parameters as higher dimensions for the parameter less, and then take the projection down. That's how that's proved. and then we're done. We basically now have this, which is exactly what we want. Except for various reasons, you'd like to assume that this is closed. I think so, it was convenient to assume this is closed. But then at the end, you can just say, well, I don't really need that it's closed because if I can do this when it's closed, I can do this for arbitrary. So the official separation is right here. If I have a subset that's definable in dimension M with a limitation Q, then I can write it as the form set of QUM, where U is a seven tuple. That's that's what how separation works. And then finally, the theorem we want is that there's a structure M, which has the same thing that we started with. Indiscernibles are the same. This tupling is the same, but limited separation slash M we get as opposed to that very special thing we had before. And the number seven is very important here. I mean, it's not really. The point is, it's got to be a small number, some particular number. And by the way, I have no idea how to make it one or two or something like that. It seems like you need something like that. You know, it doesn't make much difference for the reversal. Okay, and that's the indiscernibles just repeated without change. And that's what this set is, if you remember. We defined it before. This is some talk about that we already had before about how I go into section 8. Remember, I have to at the end of section 7, there was a question of how you start section 8 that we did 2 weeks ago, and I needed to carry a little bit more from section 7, and I think we talked about that. That's already in the lecture notes stuff. So, uh, all right. So I think that I'm done, Andreas.